Okay, so these are kind of new results that I have. They're undigested, and there's a couple surprising conclusions that are very preliminary. And I would like to say that even though I have many wonderful collaborators, I'm the one who's responsible for what I'm going to say here today, and welcome your feedback. So, a little bit of a background here, the famous BPT diagrams for emission lines. They're a way of diagnosing the ionizing source in emission line radiation coming out of galaxies. And there are three versions. They all have the same y-axis, which is O3 to H beta. X can be N2 to H alpha, or sulfur 2 to H alpha, or O1 to H alpha. So I'm going to be making extensive use of these diagrams in my talk. All right, so the sample is MaNGA, and here are the various cuts that have been used, basically face-on, pretty nearby to get good resolution, high signal-to-noise AGN thrown away, and the spectra that I'm using are just two per galaxy, the spectrum in the Sloan equivalent Faber region and the spectrum in the entire MaNGA bundle. So here's what the sample looks like in an effective stellar star-forming main sequence diagram. We're using here C4000 as a proxy for star formation rate, stellar population age, and this is mass. Just reminding you that our general picture is that galaxies increase in mass and quench. So in a general way, objects follow the arrow. Okay, so here is a twin diagram, a BPT diagram for the same sample. And I'm coloring here by the specific star formation rate based on the H alpha. And this happens to be for the fiber. So you'll note that there are subpopulations here. This population here is strongly star-forming, and we can call it the star-forming main sequence, corresponds to this. And then there's a more aged population here, which goes by a couple of different names, Liner or Lyre, and its ionization source is different and somewhat controversial. I'm not really going to talk about that. I'm going to concentrate on this region of the population today. Okay, so this is a repeat of that previous diagram at higher scale. And now let's color by another number. Oh, well, before moving on, I'd just like to point that we're moving generally from blue to red, which means we're moving from high star formation rate to low star formation rate. So this suggests that we should interpret this diagram as an evolutionary diagram in which over their lifetime, galaxies generally evolve from this part of the diagram to that part of the diagram. So we can confirm that in a couple of different ways. We can color by our stellar population surrogate for star formation rate, that's C4000, or population age. We say the same effect. And we can color by mass and see the same effect. So all of these trends, star formation rate, mass, they vary systematically during the galaxy's lifetime, and they're all showing or suggesting the same sort of pattern here. So it's natural to assume then that this is kind of an HR diagram for galaxy evolution. This diagram is interesting because if you look very closely, you can see that in this evolutionary stage, moving from star forming to quench, there's a segregation of color points. There are green points here and there are dark red points here. That corresponds to mass. So one of the things we're learning is that there's a weak but significant mass dependence of the way galaxies move and evolve through this diagram. It's not a very big effect, but it's important because it helps us understand the sorts of objects that fill in this troublesome region here. And it looks as though they're, in general, objects with lower mass. Okay, so moving on. Let's use our picture here of evolutionary tracks, and we have 3 different tracks here colored by the color and mass of the points that move through from star-forming to quench. Okay, so these DPT diagrams are kind of weirdly analogous to HR diagrams in the sense that there's a star-forming main sequence, and galaxies turn off at different points corresponding to their mass, and then they move up another branch in the diagram which corresponds to an aging stage. All right, so these diagrams have all been using nitrogen to H-alpha on the x-axis, and for completeness, I'll just show one picture using sulfur on the x-axis, and you can see it's more complicated. Various people have noted that there's a feature in the sulfur diagram down here that doesn't seem to appear in the nitrogen diagram, but now that we're coloring by mass and interpreting mass as an evolutionary stage, it's natural to interpret this as a loop, an evolutionary loop, and it occurs in sulfur, not nitrogen, because the models show that as we increase the metallicity with time, the behavior of sulfur isn't monotonic, so it causes it to make a loop. Okay, just for completeness, I've said that this is a sample that doesn't have any AGNs in it, and I'm showing you where we have a novel way of locating AGNs based on oxygen-3 luminosity and equivalent width, and this is where our AGNs show up in this sample, and you can see that they generally lie high above the main sequencing path, as you would expect from previous work. Okay, so now I want to turn to the question of stellar population problems. So we've spent a lot of time studying the Blick indices in MaNGA galaxies, and we have a way of correcting each index, not only indices, but also colors and mass to light ratios, using a metals parameter. And this is purely empirical. The metals parameter is logarithmic, and it's basically the log of the mass minus half square root, half the log of the half mass radius, Rm50. And the value of this exponent here, 0.5, is soft from our stellar work, but we know it must lie somewhere between 0 and 1. I'll come back to that. So the next 3 slides, this one and the next 2, are showing you examples of what the plots look like before and after correction, and the stars are colored by this metals parameter. So red is metal poor and blue is metal rich, and in this plot you can see a lot of scatter, and after correction the ridge lines snug right up and are much tighter. We can do this in all the indices, in all the photometry, all the way from FUV to I4. Okay, here's another example of an index diagram, an important diagram which has been used to diagnose the presence of starbursts. I'm making a small point here that before correction there's some scatter in the T region here. This is Balmer absorption versus D4000 in the fiber being used to find starbursts, as I say, and correcting these indices for metallicity effect should be done before looking for starbursts. Okay, and finally the last slide here of this example is showing G minus I colors before and after correction. Okay, so now let's move on and make similar plots that compare the emission line properties to, in particular, to D4000. And I'm looking here for 2 things: the general overall tightness of the relation, and also trends as a function of our metallicity parameter, this metal parameter. So this is the first plot, and it's a plot of the H-alpha specific star formation rate versus another example of star formation rate or stellar population age, and that's D4000. And it's really remarkable how tight this relation is. There's a little bit of scatter here due to low metallicity, and actually you don't see that if you look at Sloan, so we've not corrected for it. At some level, the MaNGA and Sloan samples are not quite identical in these respects. Okay, but this plot tends to confirm the fact that to a high degree of accuracy, SSFR and H-alpha and D4000 are the same number. Okay, here's a selection of different plots here. This is N2 divided by its luminosity expressed in, it's a specific star formation rate based on N2. It's obviously not really a star formation rate, it's N2, but the units are the same as we've been using for H-alpha. And the same thing is true here. This is O2, O3, and sulfur 2. And so draw a couple of conclusions from plots like this, again with coloring by metallicity. Okay, the line luminosities, all the line luminosities are pretty well correlated with D4000 and hence with star formation rate or stellar population age. The scatter is mainly due to metallicity variations in the H2 region parts of the diagram, especially here O2 has particularly large scatter. The metallicity of the gas is related to the metallicity of the stars, and the signs of the metallicity dependences generally agree with what H2 region theory predicts for star-forming galaxies. Okay? So now we can look at a similar diagram for emission line ratios. Ratios are important because they figure in many of the various formulas for measuring the metallicity of gas in various combinations. So an important ratio, well, I've taken very basic ratios here, starting with nitrogen and sulfur. My talk is going to compare results from nitrogen and sulfur on the one hand to results from oxygen on the other. So I'm starting here with nitrogen and sulfur. And here is nitrogen to H-alpha. We are interested in the star-forming part of the diagram, which is here. And we see a nice trend. It's pretty smooth and monotonic. Here is sulfur to H-alpha, a nice trend, but in the opposite direction. And if we subtract, we see a really nice smooth and monotonic trend, large and positive. This is well known. Many people have used the ratio of nitrogen to sulfur to measure gas metallicities, and it's going to turn out that this is my favorite number also. Okay, let's move on. Now we compare similar results for oxygen 2 and oxygen 3, and this might be the most important slide in the talk. Same plot, O2 to H-alpha versus star formation rate. And for O2, what we see is a nice relationship, but it doesn't look like it's particularly monotonic. There are a bunch of red points here clustered in one spot. The concern I have is with O3 to H-alpha, in which really there is a spread, but there's no color change across the spread. So how would you be able to infer our stellar metallicity from this residual? I don't think you'd be able to do it. Here's another ratio that people often use, O3 to O2, to measure gas metallicities, and that's a very confusing ratio according to the data set. It'd be hard to conclude much from it. Okay, so my main point from that slide is that the metallicity behavior of O2 is largely monotonic, but that O3 differs. So here, oxygen abundance is a brief history. Why is oxygen important? It's the most abundant heavy element, et cetera, and jumping to the bottom of the slide, lots of different combinations of oxygen with other lines have been used to measure gas phase metallicities. Oxygen has been the workhorse element for that, but results have not been consistent, and workers in this field are very aware of this and concerned about it. Okay? So there are two oxygen scaling laws. One is the mass metallicity relation, which is the mass versus the mass of, the abundance of oxygen Z versus the mass of the galaxy. And then there's the fundamental metallicity relation, which takes that to the next step and adds a term here in specific star formation rate. So the thought is that this coefficient is negative, reflecting an anti-correlation between the star formation rate and the oxygen abundance at fixed mass. And this is a plausible feature of actual galaxy evolution. You can imagine fresh, pristine gas arriving in the galaxy, diluting the abundances and raising the star formation rate. And that's been a popular interpretation of this observation. So the first relationship is not controversial. This one is controversial because it's been hard to duplicate with different metallicity measurements. And I want to say more about that. Okay. So here's an example from a wonderful paper by Sanchez and company, Sebastian Sanchez, comparing 12 different ways of measuring gas phase metallicity. And all of them in this picture use oxygen. And they all have the same problem in the sense, well, there are two problems. First problem is the slopes are very shallow. So when you calculate expected changes in galaxy metallicity as a function of mass here, you expect steeper slopes. And then in addition, there's 0-point differences amongst the various methods, which this whole paper is a discussion of this problem. You'll note that there is one panel here which looks different from all the others, and that's the panel that uses nitrogen and sulfur. And specifically, it uses a method combining those two lines that was developed by Mike Dopita, Lisa Cooley, and collaborators back in 2016. So I'm going to call that the Dopita method and talk more about that. Okay, so we have this metals parameter from our work based on stars, and I'm comparing that's on the x-axis here in the bundle. I'm comparing it to 3 other metallicity measurements from the gas. 2 of them are oxygen, and 1 of them is this Dopita N2S2 measurement, and this is the tightest. It's not perfectly tight, but it's quite a lot better than either one of the oxygen methods. So let's assume that the Dopita method is giving the gas phase abundance. You see a correlation with our stellar parameter. We don't know very well the exponent in the denominator of R. So let's assume that Dopita is truth and vary that exponent and find the smallest scatter. And the results are as follows. In the fiber, we find that exponent is 0.37, and for the bundle it's 0.94. That's almost just M over R. That's potential well depth. And that implies, combining these two relationships, implies a radial abundance gradient given by this number. And we can look at the Dopita measurements and our stellar measurements separately and confirm that number is very consistent with both of them. So we're getting a system here in which various information about abundances in different directions is tending to increase. This would predict that there would be contours in radius versus mass of constant metallicity, using the gas metallicity here, is showing you that in fact the contours have, as plotted directly, have the expected slope from the system. Okay, I'll skip over that. So what I want to say in the last couple of slides is that I'm worried about oxygen measurements, and is there a reason why we should be worried about them? Maybe there is. Here are theoretical surfaces in that as a function of ionization parameter and metallicity from this excellent review by Lisa Cooley and her collaborators. And the point is, look at the blue surfaces here. The point is that there's a fold. And so if you look at a particular location here, and that's all you have, you don't know whether you're seeing the back front of the surface or the front surface. And as by very bad luck, the observations run right along the fold. So I'm just wondering whether or not that uncertainty might be contributing to the difficulties that we're seeing. And you can ask the question, if you're here, are you going to make a correlated error? Because you'll either see the back surface or the front surface. How do they vary? And there is a correlated error in the sense that if you overestimate the ionization parameter, you underestimate the metallicity. And that's exactly the correlation that causes the scatter in the fundamental metallicity relationship. So there might be some physical explanation for that scatter in these diagrams. Okay, so this is my last slide, or second last slide. I've talked a lot about this fundamental metallicity relationship, and the sense is that, as I said, when the star formation rate is higher, this is C4000 upside down. So this is high star formation rate, low star formation rate. When the star formation rate is higher, the abundance is lower. And I'm coloring here by various abundances that you would, or line ratios that you would use to calculate abundances. And the four I've chosen here all use oxygen in one form or another. And all of them show this trend. This is the MaNGA data below a mass of 10, log mass equal 10. So through the main sequence, these are star-forming galaxies. From top to bottom, there is a trend in the MaNGA data that would agree with the fundamental metallicity relation if you use the oxygen abundances, or the oxygen line ratios more precisely. And here's what you get if you use our stellar metal parameter. And there's no trend. And this is what you get if you use the Doppler abundances, which agree better with our data. And again, you don't see much of a trend, certainly nothing like what we saw in the original data. So a lot of ink has been used to talk about this trend, and in general, more generally, to interpret oxygen abundances in terms of metallicities. And I'm just worried that maybe we might be making some errors here just because it's hard to draw those conclusions from those data. Okay, so I think these are my conclusions. I'll just highlight a couple of things. Well, let me just say something. You've heard me say all these things already. I'll just say one more thing. I think it's important that we brought together a measure of the stellar metallicity, which is a standard against which you can now compare various methods of measuring the gas metallicity. And the stellar metallicity might be wrong. But on the other hand, when you compare it to different gas methods which are thought to be correct, you should always get the same trends and same residuals. And it's clear from my slides here that that's not the case. These different emission lines have different trends. They can't all be correct. And then finally, I think it's important that the stellar metallicities inspire the thought that it's not just mass, but it's some combination of mass and radiance. That's the exponent that we're talking about. And so we heard yesterday from Peter Baruzzi, many models. Is it potential well depth? Is it M over R? There are papers in the literature that just say it's M, not M over R to any power. I think data like this might help clarify really what the overall structural trends are and whether potential well depth is really the case. Thank you.
Okay, questions?
Hi, Sandy. Mark Krumholz, ANU. This is very interesting, and I'm just wondering, another possible explanation I could see for why the Doppler diagnostic would be doing different things that agree better with the stars is that the Doppler diagnostic relies on this galactic concordance N to O ratio, which is well established for stars in the Milky Way, but I don't think we know how universal it is. And I'm wondering if maybe another possible interpretation is that this is really telling us about a real difference in the abundances of N versus O, and the stars are, of course, not based on O, and so maybe the reason the DAPIDA diagnostic agrees better with the stars is because both of them are looking at something other than oxygen.
Yeah, that's a really good point. I need to think much more about that. I was really horrified by these fire results today, which looked so intriguing. I will say that probably the most important element that contributes to the stellar calibration is magnesium. It creates the strongest features in the spectra, so that would tend to counterbalance your point, although your point is very well taken.
Diane, could you please step forward? Okay, so more questions? I have a... So, what would be your best proposal for figuring out what exactly is wrong with the measurements of the oxygen? Is it geometry of H2, like to sort out what track you're on? What would be the best proposal?
That's an excellent question, and I listened with great attention to the talks by our theoretical H2 region modelers, and if they could model those surfaces and the errors associated with them, that would be very interesting to me.
Okay, let's thank Sonia again.